Amazing, thank you. It's always very surreal hearing your life story explained out by someone, but yeah, so that's me. And this is a really full circle moment for me because, yeah, I did my undergrad here and this is where I sort of fell in love with fluid dynamics. And today especially is a nice one because my first paper just got published this morning. On my drive down, I got the email from JFM, so at the end I'll link to the archive, but there's now an official version as well, which is exciting. So this is work I completed at the University of Bath, supervised by Paul Malewski. And as I say, I'm now over at the University of Warwick. So I want to start off with a bit of motivation. So this is a video that I took in a lovely summer's day in Swansea. I wish I was joking, but this is August 2022, and my mum thought I was absolutely mad because I stopped to take a video of a puddle. But I think it really sums up why I care about droplet dynamics and why I care about bouncing, because there's so much interesting behaviour happening in such a small area of the world. You can see that some of the droplets are causing cascades and splashes, and then in particular I want you to try and find, so there's a few dotted about that look like they're just stationary. And what's happening there is that those droplets are in fact bouncing, and they're bouncing really small amounts, or some of them get quite high in their bounces. And in order for that to happen, there needs to be a layer of air separating the two regions of fluid. So there needs to be a constant air layer between the droplet and the bath. And if there's not, they coalesce, maybe they splash, maybe it just looks like it sits stationary and then disappears. But in particular, the regime that I look at is rebounding. So these soft, gentle behaviours where the wave field maybe isn't super large with respect to the size of the droplets. The droplets that aren't causing these big cascades are of like millimetre size. So lots of small deformation, and in particular that relates to a small Weber number in the fluids. And the work isn't just motivated by puddles. Instead, my supervisor did a lot of work on Faraday pilot wave droplets, which is what if we had a system like this, but instead of a puddle, we had an oscillating vertically bath. And you get all sorts of interesting dynamics there. But most of the models that looked at droplet rebounds disregarded the air layer. If the droplet is millimetric, the air layer is orders of 10 to the 7 or 10 to the 7. So really, really small. They can normally be disregarded, and a lot of assumptions are made on how that interaction happens. So my work is filling the gap, not only in our understanding, but literally by including this air layer into the model dynamics, can we get a reasonable approximation of what happens without needing to do any sort of assumptions. So yeah, I'll link back to Faraday pilot waves right at the end, but that's a good idea of where we're trying to get to. So let's simplify it down. We don't have a big puddle. Instead, what we have is an infinite deep bath of some given fluid. We have an air layer above it, so an upper half plane filled with air. And in particular, we only really care what happens beneath our droplet. Away from our droplet, we consider the air to be stationary and at ambient pressure. So we have two regions of fluid. One's a lower half plane, one's a sphere, and we have a thin layer of air. So we assume that the behavior of the air only really matters when the two liquids are close to each other. So we have three very different geometries to consider, so three very different regimes, which means we need three different methods to reduce them and to consider them. So throughout this talk, and there might be some errors on slides because it does get complicated, but hopefully I refer to anything in the bath with the subscript B, anything in the air with the subscript A, and anything in the droplet with the subscript D, just for clarity of notation. So what I'm going to do is I'm going to break these three regions down into three different systems and then try and combine them all together. And this is sort of how I did it. So starting with the liquid, and in particular the bath, but this is more generalized to the bath or the droplet, we're looking at reducing it down to an interfacial system. So I only really want to resolve evolutionary equations for that interface between a given fluid region and the air. So here I've used alpha, so this could be in the droplet, this could be in the bath. So we have a standard Navier-Stokes with respect to gravity, and then at the interface we have our kinematic boundary condition and also a surface tension, term coming from here. So we have our pressure jump both in the bath regime and then in the air as well. So the goal with this work is following a method developed by Diaz and Diachenko. And how we're going to do it is we're going to assume that the velocity, can be broken down into a predominantly potential flow with this small vortical correction term. So this is the 2D derivation of the decomposition at the top. Sorry, if it was 3D, that would be a curl instead of a grad nabla. So essentially we're saying most of the fluid throughout the main bulk is mostly irrotational, and then there's this small viscous term near the surface is essentially what this means. And if we take this assumption and we try and eliminate this psi term using a quasi-potential approximation, what we end up with is Laplace's equation in the bulk of the fluid, where you have this horizontal Laplacian plus some dz term. And then your free surface equations break down into these two nice PDEs. So here we have the evolution equation of the potential, which is dependent on the pressure, the gravity, the surface tension, and the viscosity of the fluid. And then we have the evolution equation of the interface. So our eta here is our interface, which is some z derivative of the potential plus a viscous correction term. So we need to do something kind of complicated because we're taking dz on the interface, where obviously z you would assume would be set to 0. So in order to do that, we do a Dirichlet to Neumann map that I'll talk about a little bit later on. But essentially what we've done here is we've reduced our system down into solving Laplace's equation in the bulk, and then using that solution of the potential on our interface, and then we can resolve these two equations rather than worrying about what happens in the depth. In the case of the bath, we are assuming decay in the thing, so we are in a deep bath regime. Then we need to have a look at the air layer. So what we have here is a thin layer of air where we have two moving boundaries. So we have A to B is our interface of our bath, and A to D is our interface of our droplet, and we're assuming those can evolve over time, given that they're liquids. So away from the droplet in the far field, nothing really happens. It doesn't really affect the dynamics of the rebound. So what we're assuming is that there is some region that might change size as the droplet rebounds, where lubrication effects start to take place. So we have a very long, thin region, but the width of it and the height of it is going to evolve over time. So we set some horizontal boundary where sort of the approximation that the aspect ratio is sufficiently big disappears at some R star outwards away from the center of the droplet. And then we also, in order to use this approximation, we are assuming that things are axisymmetric. So that is one of the limiting factors of this model. Annoyingly, is that we're still working in an axisymmetric regime, but that does give us a lot of things to manipulate. So if we take this approximation of our air layer and we resolve the fluid within the air, we end up with a thin film equation, where our flux term is dependent on pressure, and then also the velocity jump at the top and bottom of the region. In most of the modeling, the contribution from the velocity of the droplet is so small that it can be disregarded as well. So really, we end up with either just this main term or, does this have a thingy on it? No. Yeah, we end up with just the main term at the front. So we end up with Poisson flow in the air, which is quite nice to resolve. And in particular, when we look at an axisymmetric problem, this equation can be resolved for the pressure. So the sort of trick of the lubrication-mediated method that I'll talk about in a bit more detail in a bit is essentially this page. The fact that we're assuming that the air layer can be considered as a thin film means that we're able to kind of pull out the pressure term and feed it into the evolution of the two interfaces. So throughout this pressure term is really what's sort of driving the dynamics. And in particular, it will relate back to this is the pressure in the air, so it's going to relate back. So we need some way to match between the pressure in the air in the interface equations and this pressure in the air from the thin film. The droplet then we take using the method from Diaz and Lyachenko that I mentioned earlier. So we resolve using a Helmholtz decomposition. We assume that it's weakly viscous, so mostly irrotational with a potential plus some viscous component. But now we're talking about either in a sphere or in a disk, depending on if you're working in 2D or 3D. So we switch our frame of reference to polar coordinates centered about the droplet. So there's throughout all of this work, there's a lot of, what if I consider this in isolation and how do I match it back together later, which to me feels very like a jigsaw puzzle, which I quite like. So to resolve the droplet, we consider the center of the mass of the droplet to be the origin, and we talk about the interface outwards there. So switching into polar coordinates for that. But regardless, we attain the same set of equations. So the form of the top two equations here is nearly identical to these two equations here, with some correction because we're shifting our coordinate system. And in particular, the A to D term, the evolution equation for the free surface, so this A to zeta, whatever number that is, D term, I think it's a zeta.
Zeta.
Yeah. The squiggles all look the same to me, and it's really bad. So you can see that there's this 2 new, which is the viscous correction term, but now we have a surface Laplacian and of both the interface and of the potential, whereas before that term was just the surface Laplacian of the interface. And that is a result of the geometry that we're in. Here we're taking curvature, again, as this surface Laplacian for the full general system. So how do we resolve that? Numerically then, we need to consider, depending on whether you're in 2 dimensions or 3 dimensions, some sort of decomposition. But if you assume, in this case, the spherical harmonics, you can resolve from that system of coupled equations, you get out a simple ODE for the coefficients. So in 2D, these are just Fourier coefficients, and in 3D, they're spherical harmonics. And there was something else about this page. Yeah, this is actually a really nice result, because whilst it was already sort of done in the literature, I think there's a version of this in Lamb's book from 1921. Deriving it typically goes via an energy argument, and we got there from these equations, which I'm quite proud of, because that took about 4 months of hard writing to get to. So it does just kind of additionally validate where we got to. But yeah, you essentially have an evolution equation which depends on the lambda, which comes from our viscous term. This omega comes from our surface tension, and then we have our pressure forcing, which is the pressure outside of the droplet acting inwards again. So this will be some relationship from the air, which will act symmetrically on the bottom of the droplet. So we have, in isolation, a way to evolve a deforming sphere. We have a way to evolve a thin layer of air with 2 moving interfaces, and we have a way to evolve a free surface of a deep bath with some pressure coming from above. So we need to couple it all together. But just to write it out, because you've got to have one slide that's just pure maths, I think it's obligatory. So this is the full system. This is the lubrication-mediated method for droplet rebounds. So here on the top, in this top bubble, we have the baths equations, then we have our thin film, and then we have our droplet dynamics. I've just shifted the notation a little bit, in particular where we used to have the derivative with respect to z in the evolution of the free surface. We now have this capital D, which is representative of the Dirichlet-Neumann map, which essentially takes the perpendicular gradient and maps it onto the interface. Then we have our thin film equation, which is written in a slightly different form, because where we had the evolution of the height of the bath before, we now say that the height of the bath is given by the positions of the interfaces. And we know what the time derivative of the interfaces are, so we can swap them out. So if h was a to d minus a to b, we've swapped them out with this fb and fd. So we're able to kind of couple the equations together by taking a step forward in time, figuring out where our interfaces are, figuring out what the time derivative of our interfaces are, and then smushing it all back together, which is a lot of back and forth, but is quite cool. And then finally, the sort of new equation that I snuck in at the end is just F equals ma to evolve the position of the center of mass of the droplet. So as it falls, we're saying that there is some force which is being generated by the pressure in the air beneath it. We're disregarding drag because we're looking at this small, slow rebound system. So all we have is the pressure and gravity affecting the dynamics of that droplet as it moves. So that's just this final equation here that I've snuck in. But this is the full system, which is quite nice. I like it. So how do we go about evolving it? As I said, we need to kind of match these pressures together. So the way that we go about doing that is starting from no pressure in the air at all when the droplet's sufficiently far away. We need some way to kind of switch on the lubrication method. In theory, because the thin film evolves with, there's a h cubed term in the height, sorry. There's an h cubed term in the height, so when it's far enough away, the lubrication layer will switch off. But that's not as interesting as imposing some cool conditions to make it work. So we need to do some matching between these three systems to get them to work together. So first thing, as I said, we compute the pressure in the thin film and then impose upwards and downwards. Obviously, the interfaces are computed separately, and in particular, the interface of the sphere or the disk is computed with respect to polar coordinates, so we need to have some matching between, in MATLAB, the discretizations there. But in theory, we just match up and downwards. Then we need to talk about the contact time. So whilst the droplet is far away from the bath, there is no effect of the air on the system. And the way that we go about solving that is essentially just say, when the droplet is sufficiently close to the bath, turn on the air pressure. And there is some nice theory done on what this value should be. Numerically, we found that the system was actually quite invariant to that choice. I think we scaled from 0.1% of the radius all the way up to 10% with very little effect on the overall system, which was quite cool. But yeah, essentially, as soon as that droplet is within a certain height, and because it's axisymmetric and we start with a flat bath, it will always be the center that touches down first. Once that hits a certain height difference, we switch on the air layer and we start computing the pressure within that. And then once it rebounds and goes away far enough, we switch it off again. Outside of that, we assume pressure effect is zero, matching to whatever the ambient pressure is. Obviously, the first point of contact is going to be a single grid point at zero, or a singularity. So how do we go about ignoring that? Well, numerically, we just kind of wait until the region is wide enough that it doesn't break the code. But in theory, we update the horizontal width with this same condition. So because of the way that dynamics of droplets work, we are pretty confident that in the regime of small interface deformation and these nice vertical rebounds, that the lubrication regime won't have sort of a pinch region and then a region that's too wide for the system. So it will always go from the origin outwards in a nice way. So we just say that once you move outwards far enough radially from the center of the drop, that this condition is no longer met. That's your horizontal boundary. And the nice thing about this is that can be updated dynamically. So we go from having a region that does not compute any of the air layer to letting the system derive its own boundary. And we see this lubrication region spread during the impact and then sort of slowly peel off the droplet as well. The nice thing about this is that we have no further input. Once we start this system running, it kind of decides for itself what this lubrication regime is looking like. Whereas up until now, methods have sort of imposed the shape of the pressure profile, the width of the pressure profile, and good estimations have been done comparing experimental and numerical results, but it was all imposed on the systems, whereas this is completely freeform with respect to that. So I want to show you some pretty pictures, because this is my favorite part. So here we have a run that is a 2D deformable droplet. So this is fully symmetric. So we're looking at a disk impacting on a deep bath. At the top, we have the full domain of the bath with a droplet impacting. Down the bottom here, we're talking about speed. So you can see that the blue dot is moving along just to show you where along the impact we are. And then the bits that are interesting and novel are these pressure and height plots. So you can see that they're flipped. So 0 is in the middle of these two plots, moving out to minus R and R. But because the system's symmetric, I've just flipped the plot around. In particular, if I let it restart, you see that we go from 0 pressure, and then we get this very sudden spike, and then it quickly flattens out. And you see that throughout most of that lubrication layer, it is quite a flat pressure. There's not a lot of oscillation happening. There is a slight peak at the edge of it, and then a quote-unquote negative pressure region at the boundary. And that corresponds to where the height is quite flat throughout most of the impact, and it narrows. And what's happening there is the droplet and bath are sort of suctioning together right before they peel off, which is not shown on that page, which is annoying. Where do I want to go from here? Yeah, okay. This is the same rebound as the one I just showed you, but now we're comparing it to a series of different runs. So the video that I showed you is the curve in blue here. So we have time evolving on the horizontal, and we have vertical height on the vertical. And we're plotting the position of the free surface, the south pole, center of mass, and north pole of the droplets. So you can see that the bath is completely stationary until there is a really small, like this pressure, this height difference is tiny in comparison to the size of the droplet. And you see the impact of the bath deforms with it and then slowly peels off. Additionally, plotting here then is the solid case, so taking the exact same droplet, so the same liquids and same impact speeds and size, and then making the droplet solid by essentially not allowing the droplet to deform. Bless you. Yeah, so by not allowing the droplet to deform, you're able to get a solid droplet with the same sort of behaviors, so we can compare quite nicely. And then the green lines on this plot are direct numerical simulation, which is a CFD method done in Basilisk by Radu Ciprianu over in Warwick. So the method for DNS has been sort of widely accepted and used in the literature. And the idea with this is sort of comparing like for like to see how we do against sort of current standards. We get quite close matching, which is delightful. The fact that the DNS is a lot more sort of jagged, I think, comes about from the fact that the resolution that we're getting in our system is very, very high. DNS is incredibly expensive. The run here took, I think, on the order of a few days, and we're only getting a few grid point time slices because to save that system is very computationally expensive. In contrast, I'm saving a 8,192 squared grid over 2,000 time steps, and it ran in 20 minutes. So quite a different scale that we're looking at, quite a different level of resolution. Obviously, there are some dynamics that I'm missing that are captured in the DNS, but that's the contrast that you pay off. And in particular, you can see this when I plot the surface plot of the height of the air layer. So on the left here, I have my model, the lubrication mediated model, and on the right, you have the DNS. So this is, if you think of the y-axis as the center of the droplet evolving over time, and radially outwards, and this is scaled with radius, so 0.4 is 0.4 of the drop. There is clearly good matching, good agreement in the sort of overall quantitative behavior of these regimes, but the resolution that we get, again, is quite different. But we're still able to pick up similar behaviors. There is this near flat region throughout most of the impact, and there is this darker region which corresponds with a thinner height, which we think of as these pinching regions at the edge of the lubrication layer, and then finally at the edge of the end of the rebound, where you have essentially the lubrication region has kind of shrunk inwards to the center of the droplet, and you're having this final pinching effect before the droplet moves off. And we don't have a method of capturing coalescence. There is no way for our two interfaces to touch beyond just my code breaking. But in theory, this suctioning effect at the end, if that was to overcome the net upwards force on the droplet, that would be where you would see coalescence happening. Or if our droplet impacted too large, you might see it in these pinching regions at the side, which would cause bubble entrapment, which is of interest in the literature, just not in my work. But yeah, getting this plot was a very happy moment for me in my PhD, because we're seeing clear regions of behavior that up until this point were only captured with DNS, and we were able to do it with our reduced order model. The nice thing about this then is it tells us overall behaviors of the droplet dynamics. So as you saw in that video, there is this very fast spreading out of the lubrication layer. So we think of this as our initial impact happening. Then you have this slow shrinking of the lubrication layer, and that corresponds to the droplet moving downwards and upwards. So rebound, if I come back here, you see that we hit 0 at about 1.7. So this is where, for all intents and purposes, the droplet turns around now. And that's once that region has already started to shrink. And that corresponds with this sort of thinner part of this height region where it's finally starting to shrink off. And then finally you have detachment. And we could run the code much longer than this, and the droplet does just fly off into space before gravity takes over and it starts to pull it back down. But in theory, we're able to accurately capture a droplet rebound in 2D and compare it to DNS. The main problem with the 2D system, though, is it doesn't compare well to axisymmetric 3D. So when we look at sort of a 2D droplet, essentially what we have is an infinite cylinder that's bouncing. So the suction effect on the droplet has a much larger impact than it would on a sphere. So the next sort of port of call was obviously to consider a 3D model. Can we fully extend this and start comparing to experiments? Limitations of that is the thin film equation becomes a lot more complicated to resolve. Instead of just integrating out with respect to x to find that pressure in the thin film equation, we end up having to do something a bit more complicated in R and being a bit more careful with how we resolve it. So where we got to, oh no, there's one more. What have I got here? Sorry, this is the corresponding pressure to this height profile. So you see the height, or the shape of the pressure profile in the air layer in the 2D system, and it matches with what was currently accepted in the literature was this top hat profile. So a nice flat region in the middle of the rebound, and then a slow decay to 0 on the outsides. And you can see here the suctioning effect is corresponding to this pinching region of negative pressure. And again, the suctioning on the wider part corresponds with this like region of negative pressure. And I'm saying negative in quotes because obviously there's an ambient pressure in the atmosphere that it scales down to. Yeah, sorry. Going back to the 3D stuff. No, not going back to the 3D stuff. Sorry, I should know my slides better than this. Right, starting again. The question is, where does this work? What regions of impact size, impact speed can we consider this to behave? And the answer is quite a wide region. So if we look at some classic metrics of droplet rebound, in particular looking at pressing time, which is how long the droplet is quote unquote near the bath, and in particular, how long does the droplet spend below what would be z equals 0, the maximum depth that the droplet achieves, and then also the coefficient of restitution, so speed out over speed in. So here we have a sort of region of applicability of this droplet, so in Reynolds number plotted, and then we have Weber number corresponding to the different colours, and Ornesorg number corresponding to these different lines that you see. So you can think of Weber as sort of increasing speed-ish, and you can think of Ornesorg as a fixed radius. So the larger the radius, the smaller the Ornesorg number, I believe is the correct way around. Yes. Finally, we have the circles here are the lubrication-mediated deformable droplet, the triangles are the DNS, and these squares are the solid case. So this really just highlights that the coefficient of restitution in the solid, in the solid case doesn't match up with deformation, showing that the deformability of the sphere does make a big impact on the behavior of the rebound. And we think in large part that is because of the ability for the droplet to deform adds some uplift to the rebound dynamics, rather than just all of the energy in the system being absorbed by the bath. I haven't done an energy argument to prove that, but that's just my standing hypothesis. But what you can see here is that we're getting relatively good agreement with the DNS methods across the scale, except for looking at sort of pressing time and on the high Weber number. So we lose a lot of our, not accuracy, but just matching to DNS methods when we start looking at the fast end of the dynamics, which we think makes sense because a lot of this assumption is deformation is small, and once you start having more violent impacts, you expect the droplet to deform a lot more than this model can handle. So the best region of applicability is in that sort of medium to low Weber number, medium to low Ornesorg region. So small droplets moving relatively slowly. But overall, it's quite a wide range of applicability. Now we're on 3D. Amazing. Resolving the system in 3D, then, we really wanted to move towards, is this accurate when compared outside of a 2D system, when you start looking at comparing to experiments or comparing to sort of how you would physically expect a droplet to behave. So numerically, we managed to get, contextually, we got to 3D in the final year of my PhD. So we got to solid rebounds in 3D numerically. The theory does go to the full deformable system matching. But here we have a solid sphere impacting on a deep liquid bath. And what I think is particularly interesting is whilst the dynamics overall are the same, you see a lot more of what you were expecting. So a much wider, flatter region of pressure when that droplet impacts. In a second. Thank you. So it comes a lot flatter, and whilst you do see this pinching region of a slight high pinch and then a low region, it's nowhere near as drastic. However, the pinch off right at the end, if you capture that, is a massive spike of negative pressure, and that's because if you think of geometric spreading of a 3D droplet, right, you have this ring of negative or pinching region coming into one area rather than just two sides coming together. Numerically, though, this is a lot harder to compute, so this takes quite a few hours to run, and that in large part is because we're now resolving. Why is that? The thin film essentially takes a lot more time to resolve, I think was the reason. And because we're working in radial coordinates, we can't use the same pseudospectral method that we were using to solve the 2D system, because we're no longer in a periodic domain. We're now looking at a domain that's 0 to R. So we have to shift to a more general spectral method that I think we used Bessel methods for this. So yeah, there are some pros and cons with switching between 2D and 3D. The benefit, though, is that the matching that we get to current literature is very good, which is fantastic. So this is a plot that compares our results are in the circles, and then the DNS is the same methodology, but now for the 3D that we had before. And the KM here is kinematic matching, which was this assuming that the pressure transfer happens sort of instantaneously between the bath and the droplet without considering that air layer. So the current accepted standard of reduced order modeling for this system. And what we're seeing is very, very good agreement across the board with the behavior, except that final plot, disregard that final plot. No, but even within this system, we're still seeing really good agreement with DNS and kinematic matching. And the delightful thing with this is these results in this paper, which is fantastic for solid rebounds, was also validated with experiments, which means through adjacency, we have good agreement with experiments, which is delightful to see. So in terms of sort of future directions that this work could go, one of them is getting that 3D droplet deformable, and incorporating that numerically, which is a sort of computational issue and complexity that we want to resolve. Because the 2D model runs so quickly, we want to keep that level of computational cheapness to it without sort of sacrificing accuracy. And then the other sort of interesting direction would be, what if we get oblique impacts? And could we get droplets that move tangentially? That makes the lubrication layer a lot harder to solve, but it is an interesting problem, especially when we go all the way back to those original motivation that we had for this problem, which was the Faraday rebounds. So if we oscillate the bath vertically, we get bouncing behavior. We know that our model can capture a single rebound, so can it capture multiple? Why are none of the slides the ones I think they are? There we go. So this is the 2D model of a deformable droplet bouncing stably periodically on an oscillating bath. So if we add this shaking turned to the gravity, which simulates shaking of the bath itself. We get this stable behavior. So you see really quickly it goes into sort of a high bounce and a low bounce in a stable period regime. So we're able to capture bouncing pilot waves. Can we capture walkers as well? Essentially, can we, if we added a translational movement into this, could we accurately use this model in things like pilot wave dynamics across the board? And this is possibly my favorite video I've ever made, which is just fun to watch. Yeah, so that is it from me, I believe. Yes, that is it. So we have 2 papers out there. One of them is now available on JFM in Rapid as of today. So you can find the full derivation of the general model in lubrication-mediated rebounds off fluid baths. And if you are interested in a more thorough analysis of how the model compares in 2D to DNS, that is currently in submission somewhere, but it's on archive. And that was work done with Radu Cimpianu and my supervisor. But yeah, that's it. Thank you.